Perlman today, our distinguished speaker. She's invented several protocols such as spanning tree, working on TRILL now. I've read this book in college. I think a lot of you guys have. It's a really great book. And we had some security meetings early this morning, and a number of the people had read this book and also really liked it. So these are some good books. So we're also going to have a roundtable after this meeting with the cameras off. If you guys have any more confidential questions you want to ask without the cameras. I had a meeting earlier scheduled at 3:30. It has to be canceled because Radia has to leave before 4.
Okay. So, hello. So, yes, the title is Routing Without Tears and Bridging Without Danger. So, like, a obvious question to ask is like, well, what's routing and what's bridging? And so I'll talk about that. And there's a lot of people that think they know, and you sort of can't really know without knowing that the question itself doesn't make any sense. But I will explain it all. So, yeah, the first thing is, what are bridges and routers and switches? And so there's a myth that people tell me often that bridges are kind of simpler, and they were invented first, and then routers came along. And then, of course, when switches came along, they were like this revolutionary new kind of technology that replaced bridges. So these are all like myths, but I'll explain to you how they came about. So before we get to RBridges, which is like this TRILL stuff that I'm going to be talking about, let's sort out what bridges, routers, and switches are. So basically, you start with the definitions from OSI reference model, just sort of helps you kind of understand it, where there's layers of networking. Now, nothing is ever, really built with these layers exactly, but it's just a way of kind of thinking about the problem. So layer 1 is the physical layer. It's sort of the hardware, what's on each pin of the connector. Layer 2 is data link layer. It's how you get a message to somebody who's on the same medium as you. It's sort of how do you signal that it's the beginning of a message? How do you put in checksums and things? So Ethernet is an example of a layer 2 protocol because it's all on the same shared medium. Layer 3 is the network layer, where it does routing and it computes a whole path and forwards the packet across many links. Layer 4 is end-to-end, like TCP and UDP, which numbers messages and recovers lost messages. And layers 5 and above are boring. That's my view of networking. So the definitions, a repeater is a layer 1 relay. It moves things around at layer 1, which means it just sort of reads a bit, cleans it up, and forwards it on. A bridge is a layer 2 relay, and a router is a layer 3 relay. So now you know. So if you're taking a quiz, you know what to write down. But if you kind of think about it for a minute, it's like, I just said that layer 3 was the thing that computed paths and forwarded packets, and layer 2 was on the same medium. Why is there a layer 2 relay? So if I were defining the world, there would not be any such thing as a layer 2 relay. If you're going to forward things, that's layer 3. And so this troubled me for a long time until I finally, sort of my definition of layer 2 versus layer 3 is that there wouldn't be any relays in layer 2. Layer 2 is only neighbor to neighbor, and forwarding is layer 3. But I figured out that the true definition of a layer 2 protocol versus a layer 3 protocol is that a layer 2 protocol is anything designed by a committee whose charter is to design a layer 2 protocol. So anyway, the history of this. I was DECnet architect. DECnet, the one that designed layer 3 for DECnet, routing and so forth. So layer 3 is, like there were a whole bunch of layer 3 protocols, just like there's a whole bunch of languages today, English, French, Chinese, German. And it could very well be that English takes over the world. It certainly will not be because English is the best language out there. It's just sort of, that's what, the people you care about speaking to, because they have the most money at that point or whatever, speak. So everyone has to speak that. But I know that historians afterwards will say, why did English win out? Well, probably because, and I don't know enough about languages to do this probably because German had too many tenses It's like, no, it has nothing to do with that. So a lot of people, IPv4 has won out, but it's not because it was the best. As a matter of fact, as we'll see later on in the talk, it's actually was one of the worst of the layer 3 protocols. It just so happened, it was free. But anyway, so I was the one, what is layer 3? There's no rocket science to it. You take your data, you put it in an envelope, you say who the source is, who the destination is, throw in a hop count so you'll recognize packets that are kind of lost while the algorithm settles down. And so I was happily doing this when along came the Ethernet. And so I said, oh, that's interesting. There's now a kind of link that you could have hundreds or thousands of neighbors. And the overhead of a routing algorithm grows proportionally with the number of links. So if you took an Ethernet and did the straightforward thing of saying that every pair of nodes on the Ethernet were neighbors, then it would explode the routing algorithm because you'd have n squared links. So, what Ethernet meant to me was a new kind of link that I had to do things to the routing algorithm to make it efficient in the routing algorithm. So fine, it's a link, it's not a network. So, but the world got confused and they thought that Ethernet was a competitor to DECnet. And so there were all these trade magazines of which one is going to win, Ethernet or DECnet. At that point, IP was just this silly little research thing. DECnet was the big commercial layer 3 protocol. So I was very frustrated by this. And in particular, there was a group at Digital doing this protocol. It doesn't really matter what it was. For you historians, it was LAT. That they were building it directly on Ethernet. So I went over to them and I said, no, build it on top of DECnet. Don't build it on layer 2, build it on layer 3. And they said, oh, you're just upset because your layer is a dinosaur and we don't need it anymore. And I said, oh, but you may want to talk from one Ethernet to another. And they said, our customers would never want to do that. So they built directly on Ethernet. And indeed, they made lots of money because it was a good protocol other than that decision. They would have made just as much money if they'd built it on top of layer 3. But it's hard to explain to management that they had done the wrong thing. So at any rate, at this point in time, we had a whole bunch of protocols that were built directly on Ethernet, and you can't have a router forward your packet unless you implement the same layer 3 protocol that the router has implemented. So it's very easy to get confused. This is what a layer 3 packet looks like. And this is what a layer 2 packet looks like. They both have a source and a destination. The layer 3 one happens to have a hop count. And it wasn't because the Ethernet people didn't think of putting a hop count in there. You should have a hop count if you're going to be forwarding it because you could have loops. But it never occurred to them that anyone would be forwarding this. It wasn't designed to be a layer 3 protocol. So also in layer 3, the addresses have topological significance. It says where you are in the network, not just sort of a flat address. Whereas in Ethernet, addresses are flat. You have the same address no matter where in the world you plug in. So it's easy to confuse an Ethernet with a network instead of thinking of it as a multi-access link. Why can't Ethernet replace IP? They're both multi-access clouds that anyone can plug into. But Ethernet has flat addresses, there's no hop count, and perhaps there are some other missing features like fragmentation if you have a heterogeneous links, error messages if someone intermediate has to drop it, or congestion feedback, none of which would be necessary if it's only neighbor to neighbor. So so there were a bunch of layer 3 protocols where you put a source and destination and hop count on the packet. Wait a minute, I think I'm going the wrong way. Okay, so anyway, you can imagine I was sort of in a bad mood about this whole thing, with the LAT people being such heroes, when my manager said, Radia, we need to design a magic box that will sit between 2 Ethernets and let someone on one talk to someone on the other. And it's like, that's called a router. But of course, it won't work unless you've implemented layer 3 in these things. So basically, they wanted to build this very simple-minded device that would kind of listen promiscuously, and whenever it so it would listen promiscuously, store all the packets, and when it got the token on the other side, or when the ether was free, whatever the technology was, then you would forward it on the other side. And in addition to that, you can also learn where the stations are by looking at the source address of these packets. So that was the basic idea. But the problem is that you need a loop-free topology. You can't learn the location of the source if it can hit you from all sorts of different directions. And also, loops are a disaster. Now, in IP, layer 3, loops are not so much of a disaster for two reasons. One is there's a hop count in the header. But the other thing is that in IP, if you have a loop, one copy of the packet is going around in circles, because a router doesn't forward to multiple in multiple locations. It picks the next hop and says, Fred, you take the packet now. Whereas with bridges, you just toss it onto a shared medium and say, anyone that feels like forwarding it, do it. So if you have 10 bridges on a link and you send the packet, you can now have 9 copies of the packet. So not only is there no way to get rid of any one packet, but you can multiply every time you transmit the number of copies of the packet. So this is incredibly scary. And when this was proposed to me, I actually said, no, this is a really bad idea, don't do it. But they were going to do it anyway. But my manager said, so, you do distributed algorithms. Why don't you come up with something that does a spanning tree that kind of breaks all of the loops and comes up with a loop-free subset of the topology. And for some reason, he thought it was going to be really difficult. And he also thought he was being really witty. He said, oh, and while I've given you this impossible problem, I'm going to make it even more challenging. Make it scale as a constant. So no matter how many links and bridges there are in the world, the amount of memory necessary to run this thing should be a constant. And that's ridiculous. Linear maybe, but probably like n squared or something. Nothing's a constant. So then he went away. That was a Friday afternoon. And that evening I realized, oh my gosh, it's trivial. And furthermore, it's actually a constant. Now, it's not quite a constant. Well, the reason it's a constant is because on each link, you only have to remember the best spanning tree message you ever saw. A message is about 50 bytes. If you have 5 ports, it takes 250 bytes of memory to run the thing. So it really is a constant. The reason it's not quite a constant, just so that somebody doesn't say, oh, it isn't quite, is that one of the fields in the message is the ID of a bridge. And it's 48 bits. So if you ever had more than 2 to the 48 bridges, you'd have to actually expand the size. So it's really log of the number of bridges is how this thing does. So anyway, so bridge loops are a total disaster. So I spent like a day figuring out the algorithm, and it was so simple. It only took me like a couple of days to write it out so cleanly that the implementers were able to get it working from that in just like a week or 2. And then I had all this energy. My manager was gone for a week and completely unreachable, so I couldn't concentrate on anything else. So I spent the rest of the week writing the poem that goes along with the algorithm. So the poem is called Algorhyme, because every algorithm should have an algorhyme. So this is the poem. I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me. Then bridges find a spanning tree. So that was the abstract of the paper in which I published the algorithm. So anyway, so the idea is that you have some sort of network, and the bridges decide, basically some of these links are not, are extraneous, so it shuts them off, and they're there in case something goes down, you can start using those links again. So on this picture, one of the things I want you to notice is that paths are not optimal from source to destination. If you just have one way of getting from any place to any other place, they're not going to be optimal. So when A sends a packet and the destination is X, it has to go through this whole red path, which is really long. So you might think, well, that was a really silly spanning tree. If we had been smarter about calculating the spanning tree, we could have gotten that path better. But no, you have to break it somewhere. And if you're talking to somebody on the other side of the break, you're going to have to go around a long way. So now this was sort of just a funny story. The implementers didn't want to put in the spanning tree. It sounded scary, spanning tree algorithm. And they wanted to build this like really simple thing. And so on the one hand, I felt sympathetic with them. On the other hand, my management kind of overruled them and told them they had to do it. And so I still felt a little bad that maybe they were right, and building an even simpler device and just telling the customers don't put any loops in might have been the right solution until they sold the first bridge. Now, the first bridge was sold to like the world's most sophisticated customer. And so they had the world's simplest topology, which was 2 Ethernets and 1 bridge. And when the salesman was trying to explain it to them, they were saying, oh, but we have like all these 7 protocol stacks and we're doing all this. And the salesman said, it doesn't matter what you're doing, it'll just work. So the world's most sophisticated customer took the world's simplest topology, plugged it together, and it didn't work, and they were really annoyed. When field service went to figure out what the problem was, this is what they found. So if the world's most sophisticated customer could get this topology wrong, it's like, yes, it was right to make them put in the spanning tree. But what's wrong with bridges? So I kind of assumed they'd die out once everybody had agreed on one layer 3 protocol. Everyone does IPv4 now. There's no stacks without IP in there pretty much. So why are there still bridges? And actually about, 6 or 7 years ago, somebody showed me this Boston Globe article about how this hospital network had melted down. And, the article's all about all the horrible things that happen in a hospital if you bring the network down for days or whatever. And so, I'm reading along, and in the middle it says spanning tree algorithm. And it's like, whoa, those words do not belong in a Boston Globe article. But indeed, I tracked down the people who were maintaining this network and found out, indeed, it was a huge bridge network. Now, part of it, there's kind of a lot of folklore about this. My manager at DEC always made me put in numbers. It's like, how many hops will it scale to? And it's like, I don't know. And so it's like, clearly it won't scale to 1 million hops. Clearly it will scale to 3. Pick a number. So we picked 7. And so, the people looking at this network said, oh, I see the problem. It was more than 7 hops. It's like, no. But at any rate, I'll explain kind of why networks melt down. But yeah, I was really surprised that people are really using bridges. They're still very, very popular. And I will explain to you why it is. And so, what's wrong with just bridging everything? And if you have a corporate network, you don't have to think about anything. You just plug it together. What's wrong with it? Well, you get suboptimal routing, as I showed on the previous slide. Traffic concentration, because the links that are chosen to be in the tree will get overutilized, and the other ones won't get used at all. Temporary loops are really dangerous, and it's very fragile for a very subtle reason. With routers, there will be a link between A and B, and will be used if A and B can hear each other. So A and B keep saying, hi, I'm still here. And if you stop hearing from your neighbor, you stop using the link. Whereas with bridges, it's the opposite. The only reason I'm not forwarding onto this link is that I hear some other bridge who's sort of more qualified to be the bridge on that link. But if there's too much congestion or whatever, and I can't see his messages anymore, I will fail in the unsafe way. I will bring extra connectivity up. Why are bridges successful? Well, they're simple, fast, reliable. They're plug and play. People should get that religion, right? Just do not, configuration is bad. Now, routers have gotten better. Will bridges go away? And no, apparently, for a very subtle reason, which is that IP is not a good layer 3 protocol. The way IP works is every link has to have its own prefix. So if you were to replace your bridges by routers, and you have a corporate space of IP addresses, you have to chop up your address space you have to, which wastes addresses, and also you have to configure every port on every router to be what the prefix is. When somebody moves from one link to another, you have to change the address. And this is painful. Now, layer 3 doesn't have to work that way. DECnet, which was also the same as ISO's connectionless network layer protocol, otherwise known as CLNP, did not work that way. Basically, digital, we took the packet format from ISO. So DECnet and CLNP, DECnet phase 5 and CLNP were the same thing. So the way that worked was that it was a 20-byte address space, and the top 14 bytes were your corporate prefix, and within your corporate prefix, the bottom 6 bytes was kind of your MAC address, and that was all that you needed. So it was, the routers were, it was 0 configuration inside your own network, and you routed directly to the end nodes. But yeah, so like the way that it would work is that if you have one prefix per link and you have a corporate block of 2 star, then every link has to have a distinct prefix, whereas in DECnet, you just had one prefix and you could move around within this network, and the routers inside didn't have to know anything. Just whoever was connected to the rest of the world would tell you what the 14-byte prefix was. So if we were doing this, we would not need bridges anymore. But because we're doing that, people don't like the headache of doing all this configuration. So yeah, so that's the advantage of doing it that way. So now I will talk about the TRILL working group. TRILL stands for Transparent Interconnection of Lots of Links. And so there's a working group in IETF, and it basically uses layer 3 routing, but it still has the appearance of just one Ethernet. So we're going to accomplish almost as well as DECnet would have, but we're still going to use IP. So it looks like a bridge from the outside in the sense that it still is one IP subnet, but anyway, so it's compatible with current bridges. So if you had a whole big corporate network that was all bridged, and you had these smarter things called RBridges, you could one by one replace your bridges with RBridges, and at all times your network will behave exactly as before, except your paths will start getting better, and it'll start becoming more reliable, fewer meltdowns and stuff, but it still could be 0 configuration. So the first thing is you run a link state protocol. What's a link state protocol? First, which link state protocol? So there's the 2 obvious choices are ISIS, which actually was DECnet phase 5 routing and got adopted by ISO, and they rewrote the spec and they called it ISIS. And then IETF said, oh, we want one of them, and kind of copied it, and it became OSPF. Now, we chose ISIS as the link state protocol to use for TRILL because it's, first of all, simpler. Kind of if you look at the specs, it just is. Also, it's encoded with, so that you can add extra fields in it. That TLV stands for type length value. So it was real easy to say, oh, you want to report about 8-byte destinations? Sure, just add assign a new type value, and so we can put those into the headers, whereas OSPF is kind of hard-coded for IPv4, 4-byte address, 4-byte mask. Also, it works on top of layer 2, whereas OSPF works on top of IP, so all of the routers need IP addresses, so it's not 0 configuration. So the idea behind a link state protocol is you figure out who your neighbors are. You construct a packet I call a link state packet that says, I'm Radia, here are my neighbors, and you send that to everybody. And everyone has to store the most recently generated link state packet from each other node. And if you know if you have everyone's link state packets, you know who all the nodes are and what the neighbors of all the nodes are, so you know the complete graph. And there are algorithms for computing paths given this database. So this is kind of what a network would look like. If the network looks like that, where B and C are neighbors at a cost of 2, this is what the link state database would look like. D would say I have 2 neighbors, A at a cost of 2, and indeed it does, and E at a cost of 2, and indeed it does. So all the nodes would have this database, and there's an algorithm for computing shortest paths from that. So inside the campus, the first RBridge picks up the packet from an end node and adds an extra header on it, addressing it to the last RBridge. So it kind of tunnels it across the campus to reach the last guy, who removes the outer header and sends it along. And that way it can look like it was just an Ethernet. But rather than like with bridges where you're actually forwarding with the Ethernet, here you can add a hop count and make it a safe header. Also, well, yeah, there's still a problem with unknown destinations. So if the first guy picks it up and doesn't know where it is, then you have to send it on a tree. And I'll talk about how that is. And by the way, in this talk, I'm not just going to say this is how TRILL works. I actually found it very interesting going through the process of the working group because there's often been controversies where there's people on both sides saying, oh, no, I want it to be this way and I want it to be that way. And so for the most part, we've come up with compromises that are not ugly, that in some cases have actually much improved the design, I think. So I'll talk about what some of the controversies were and what some of the thinking was. So, and so for the unknown destinations and for multicast, you have to send it along a tree. But there's no reason to run the spanning tree algorithm because the link state database gives you enough information so everyone can deterministically, calculate the same tree. So the idea here is the first RBridge, R2, addresses it to R7, and R7 removes the header and sends it to C. Inside here, the guys here don't need to know about where C is. They just need to have a forwarding table that reaches all of the RBridges. So it's smaller forwarding tables. So what does the encapsulated packet look like? My original proposal was that all you needed was who the egress RBridge was and a hop count. And then, but for a unicast packet, the RBridge in the header that you're specifying is the last RBridge. But for multicast, it would instead be the first RBridge. And so people were saying, this gives me a headache. What do you call this field? You can't call it egress RBridge because it's sometimes ingress RBridge. And then, so some people were just sort of annoyed about it because it gave them a headache. But then eventually people came up with a really good reason for having 2 RBridges in the header. So for unicast, it's not obvious why we need the ingress RBridge, but there is a good reason for it. You need the egress in order to specify who to send it to. But if you have the ingress one, then you can learn where the source MAC address is from looking at the data packet. Because you see a data packet, you can see the inner packet has the original source address, and you know who the ingress RBridge is, so you can make a correspondence between that end node is associated with this ingress guy. Now for unknown destination and multicast, it's obvious that ingress one is useful to do reverse path forwarding when you're doing multicast, but egress RBridge we wound up using in order to select which tree to send it on. And I'll get to why we would want more than one tree in a few slides. Another thing, in order to save room in the TRILL header, instead of having the RBridge names be 6-byte addresses, which is kind of the natural thing to do, everything has a unique 6-byte ID, we have a dynamic algorithm piggybacked on the link state protocol, where everyone chooses a 2-byte nickname. So the idea is you choose, a 2-byte nickname, and you look at everyone else's link state protocols. If somebody else says, I want to be 57, and you've chosen 57, you have some sort of tiebreaker for who gets to keep 57, and the other one chooses another one. So it's sort of a very deterministic kind of algorithm. And then some people said, well, suppose we want to configure a nickname. Well, if you actually bother configuring a nickname, then you will have higher priority for that nickname than somebody that chose it at random. Now, we also need an outer Ethernet header. And the reason that we decided we needed that was because we were operating under the notion that you had a network that was full of bridges, and you're replacing the bridges with RBridges one at a time. So between two RBridges, there might be a bridge. And it would freak out this intermediate bridge if you were trying to forward something that didn't have an Ethernet header on it. So we have the inner packet, which is like an Ethernet packet, then the TRILL header, which is the ingress and egress RBridge and a hop count, and an outer one that looks like an Ethernet that is where the source is whichever RBridge is transmitting it, and the destination is the next hop. And it's useful to have next hop as well, so you don't multiply numbers of copies of the packet. Just like with a regular router, you specify the next hop. This enables an RBridge to specify who the next hop is. So that's what the header looks like. This is the TRILL header, which has the hop count and the first RBridge and the last RBridge, and then a regular Ethernet header over here that you can tell the difference between a packet generated by an end node and one being forwarded by an RBridge because the protocol type here says that it's TRILL. So you do routing just like you would with any routing protocol, but the destination that you're looking up is it's not an IP address, it's actually an RBridge. Okay. Yeah, it would be bad to have two RBridges on the same link encapsulating and decapsulating, because then you could have really horrible loops because there's no hop count anymore. So if you have one guy that decapsulates it and another one picks it up, there was no hop count there. And if he sends it out, if it's some sort of multicast. So you have to make sure that there's only one guy on the layer 2 cloud that's encapsulating and decapsulating. So this is called the designated RBridge. ISIS already does some sort of election so that there's only one guy on a cloud that's known as the designated guy. And so we'll use that in order to pick one guy to be the designated RBridge. So learning where the end nodes are, since I think like a layer 3 person, and I was remembering DECnet, the way that I assumed that it would work was that the first RBridge learns who its local end nodes are and sends that in link state information to everyone else to say, here are all my attached end nodes. But then there were a bunch of people that think like bridge people, that think like layer 2 people. And they wanted to learn from data packets because they didn't want to learn about end nodes that nobody on their link is talking to. It seemed to like clutter their database, have a whole extra unnecessary protocol and all that. So then there was like fighting for a while. And then people were saying, make them both optional. And you can't make them both optional, because if it's optional to advertise, and it's optional whether you're going to learn from data packets, then you can have some destinations that will always get flooded because someone is not learning them from data packets. So what we decided was that we would make it mandatory to learn from data packets, but optional to advertise attached guys and optional to learn from them. And I think that actually, as kludgy as it sounds, I think it's actually a great solution, because you would what you should do is only advertise end nodes that you kind of are pretty sure are really there, as opposed to anyone can transmit a packet with any source address. But if you have some sort of registration protocol, possibly even cryptographic, and you really know that that's the guy, then you would advertise those, and anything that gets advertised would supersede anything that's just sort of learned because someone happened to transmit a packet with that source address. Flooded traffic. Some traffic needs to be sent on all of the links, like unknown destinations. So the original proposal, I assumed all of those would go on one spanning tree. And then some people said, that's not the optimal path. And optimal path doesn't really matter if it's going to everybody. But, because you really have to send it on all the links. But if you're doing something where you're filtering, so for instance, you're only sending it on links that are in a certain virtual LAN, like, I will talk about VLANs later. You don't want to know, but I will be talking about it. Layer 2 has this ability to kind of color the end nodes with these things called virtual LANs. And so RBridges will say, this link has VLAN A nodes and VLAN B nodes. So there's only some of the links on which there might be a VLAN A end node. So if you have an unknown packet within VLAN A, you know it only needs to go to that link and that link. So if you just did one spanning tree, it could be like a really horrible path between the two links that have VLAN A. Whereas if you have the tree that you use has as the root the Ingress RBridge, it will be an optimal distribution path. So also with the Ingress RBridge as the root of the tree, there was another concern that people had, that packets could get out of order. So when the source is sending to the destination, and at first your RBridge doesn't know where the destination is, it will send it possibly on a long path. Once it finds out where it is, it'll send it on the optimal path. And my, my inclination when someone says, "Oh, packets can get out of order," is like, so what? And so, people say, "Oh, but there's all these important protocols that will break if packets ever get out of order." And I say, "What are they?" And they say, "Well, there's a lot of them." And and they're like really, really important. So, my feeling is any protocol that's that fragile that it can't deal with an out-of-order packet deserves to die anyway. But at any rate, so then we were kind of using per ingress trees. And then some people were saying, "Oh, that's too many trees to compute." And other people were saying, "That's not enough trees." So what that means is that they were saying, so this shows what a suboptimal tree is. Suppose these two green links are the only links that have VLAN G on it. When A transmits a packet and it's not known where the destination is, it would have to go all the way around here to get there. Whereas if instead you had a tree computed with that as the source, it would go the optimal path. Why do you want to, right, so this is when it matters to have a more optimal tree. Too many trees and not enough trees. So what does it mean not enough trees? Some people were saying, suppose all of our traffic is multicast traffic, and it's all behind one RBridge. We don't want all of the traffic to use only some of the links. So what they wanted to be able to do was have the first guy specify a different tree so that you could do multipathing of the multicast. So, so the conclusion was that the first guy gets to select what tree it is by putting into the egress RBridge on a multicast the root of the tree. And, right. So then it's like, which trees do you use? And some people say, oh, it doesn't matter. It's just something that the customers will configure, which, kind of gives me a headache, right? So I threw in an algorithm. I mean, this was something I spent like maybe 20 minutes on. So I'm sure there might be a better thing. But, well, first we had a flag for each RBridge saying, I want to be the root of a tree. But that didn't really, so you had to calculate a tree from, every one of those. And that didn't really make a whole lot of sense. Why would they care? So instead, what we decided to do, as of, like a week ago, this thing is, just little details are being worked out at this point. But it means that you can still jump on the mailing list and have your voices heard if you care about this stuff. So the idea would be that there'd be one parameter that would be how many trees everybody should compute. And so every RBridge can be configured with what they think is how many trees. But the RBridge who has highest priority gets to tell everybody else, you're all going to use 8 trees. Now, which 8 trees? You have like a priority and an ID for each RBridge. And what you do is you rank all of the RBridges according to priority and ID, and the top 8 are going to be the 8 tree routes that you're going to use. Now, if you're going to multipath, how do you know which ones to use? And so, again, you could configure it, but the trees might change as well, so that seemed kind of hard. And again, something that I spent, like 15 minutes on, so again, there might be a much better algorithm. This is the kind of thing that people who love simulations or, students that want to generate papers, this is an opportunity for papers, I think. If you observe this topology, where there's like a whole bunch of, end RBridges, all attached to one blue guy here, if you have one tree, if you calculate one tree with that as the root, it will be exactly the same tree as if you calculated all of these trees. So it would be wasteful to calculate all these trees. It would be better to calculate those. And if you want the optimal tree, you should use the one rooted at that guy. So what I suggested on the mailing list was if there are 8 trees total, what you do is you rank them according to your preference to you by saying, how close is the root of that bridge to me, and then priority and ID. And if you're going to multipath on 2 of them, you select the top 2. So, okay. Any better ideas? I don't know. It seemed. So VLANs. Oh, okay. So now I will talk about VLANs. Is there anyone here who never heard of VLANs? Okay. Yeah. I was thinking I was going to end somebody's innocence. And take great delight in doing it, because it's like the more I hear about these things, it's like, oh no. So my model of VLANs, what I kind of thought it was a way of coloring the end nodes such that VLAN A nodes could only talk to VLAN A nodes. Each, VLAN A would be one IP subnet, VLAN B would be another one. In order to talk from someone in one VLAN to another, you have to go through a router. So that kind of makes sense, but bridges can be configured so that internal links can only pass certain VLANs. So you could have something where you say, this link between these 2 RBridges, between 2 bridges, I'm willing to pass VLAN A, but not VLAN B. And so now VLAN B can be partitioned. And it might not be partitioned if you could use another path. But the spanning tree is going to calculate only one path. So, well, IEEE said, okay, calculate a tree per VLAN, which will give you kind of will minimize the probability, will make it so that you won't ever unnecessarily partition a VLAN, though you still might have something that's partitioned because there's no way to get through it. And then some people said, oh, but that's too many. So there's some sort of thing where you can have only 64 spanning trees and map the 4,000 VLANs onto all of them and whatever. But this is not terribly relevant to RBridges. What we decided was that all the internal links would carry all of the traffic, and it would be kind of the model that I understood of VLANs originally. But there's a problem, which is that it's very, very important if there's 2 RBridges on the same layer 2 cloud that they see each other's hello messages, because it's really bad if they don't know about each other, because then you can have loops. So the way you do it is you send a hello message, but you have to put a VLAN tag on the hello message. What VLAN tag do you put on the hello message? If you put VLAN A on there, it could be that VLAN A is partitioned, and the other RBridge won't see it, even though there are other VLANs that are not partitioned, and there is connectivity. So some people said, well, that's easy. Just send hellos, 4,000 times as many hellos, tagged with every possible VLAN. And then a bunch of people said, no. And so we have, so I was saying, well, look, how about telling your customers that you can, that all the inter-RBridge traffic is sent on VLAN 1, and pick one VLAN. And that one is not allowed to be partitioned. They have to configure it so that all bridges send VLAN 1. And they were saying, oh, but maybe they want to use VLAN 1 for something else. And I said, okay, pick a number, and let's do. And so they wanted that to be configurable. And then, so what we decided, this is the compromise, and this is kind of one of the most uneasy compromises in the sense that it keeps coming up. And people say, oh, I didn't realize that was what you decided. I'm not so happy with that. But I didn't want to have hellos tagged with every possible VLAN, but some people are really nervous about accidentally forming loops. So there's all these other belt and suspender things for, trying not to, noticing if there are loops and being conservative about it. But so the compromise was that whoever's the designated RBridge sends hellos on all the VLANs, because it's important for everyone to hear him. But he'll tell everybody else, on this link, I want everyone to use VLAN 3. So everyone else will then just send hellos with VLAN 3. So, and everything's configurable, of course, in this wonderful zero configuration thing. So you can configure the designated RBridge to have a set of VLANs that it supports, so it'll send hellos on all of those. But you could also configure it to not send hellos on all of those. So, okay. So another wrinkle. Oh, yes. So I assumed that the designated RBridge would be the one that would be forwarding traffic to and from the link. But then some people were saying, oh, but suppose we want to load split traffic off of the link. And so we want one RBridge to carry VLAN A and another one to carry VLAN B. So that isn't so bad. The designated RBridge selects guys and says, okay, you forward VLAN A, you forward VLAN B off of the link. So that's now called the designated VLAN forwarder. And you can have, you can't have more than one of those for a link. But then, any sort of nightmare that you might have had about VLANs, apparently it's worse than that. So it's also the case that a VLAN A packet can turn into a VLAN B packet. So you have to make sure that you don't have a VLAN A forwarder and a VLAN B forwarder where VLAN A traffic can turn into VLAN B. So, oh, right. Oh, wait. So, yes. So I was giving a talk about this, and then I was realizing, hey, not enough jokes. And so I called up my son. It was like 10 o'clock the night before I was going to go off and give a talk about this. And my son, who was very familiar with Algorhyme because he had set it to music so that my daughter, who sings opera, and I play piano, we were doing a recital together. And so she was singing all these Italian arias. And so he set it to music. So one of the arias was the Spanning Tree poem. So he knew the Spanning Tree poem. And so I said, you have 1 hour before I want to go to sleep. But if you can come up with a modification of the poem that describes this new technology, and I explained it to him, then I can put it into my talk. So I called him up an hour later, and indeed I think he did such a great job that his poem will go into the RFC. And so his poem is called Algorhyme version 2. So it's, I hope that we shall one day see a graph more lovely than a tree. A graph to boost efficiency while still configuration free. A network where RBridges can route packets to their target LAN. The paths they find to our elation are least cost paths to destination. With packet hop counts, we now see the network need not be loop free. RBridges work effectively without a common spanning tree. So so that's my son, Ray Perlman. So that's basically it. So thanks.